Welcome to the Astrophysics Podcast. When I was a kid, I absolutely loved black holes, but I didn't really know what they were. I did a report on black holes in the 5th grade where I had to give a speech in front of the class. Absolutely terrifying for a 5th grader, but I did get to learn about black holes. I learned that they're compact, massive bodies that were so incredibly dense that nothing could escape their gravity, not even light. And therefore, if you fell into a black hole, there would be no way of sending any kind of signal outside. But I was still curious about black holes. In high school, I wrote a report about them for a physics class. I learned about how the fabric of space-time is distorted by gravity, and that near a black hole, time becomes so distorted that it actually slows down for an astronaut coming close to the event horizon, so that someone further away would never actually see the astronaut crossing it. From outside, the astronaut would look like they were slowly approaching the event horizon but never quite reaching it. This concept first got me into the idea of astrophysics theory, that there is actually a field of mathematics to describe these ideas, and that you can compute how much slower time moves for somebody near a black hole. I don't know what it is about black holes that makes them so compelling, but to this day I still find it the most captivating thing to learn about. Nowadays, I teach a course at Purdue on general relativity, and I get to share my love of black holes to a new group of students every year. Being able to delve into the rich mathematics of curved space-time and use it to really define what a black hole is and how it works. If that's all I did in my career, that would be enough for me. But I get to do more than that. I also get to work with researchers on the cutting edge of black hole astrophysics to ask the latest burning questions about what kind of black holes there are out there, how massive they get, and how they form. Recently, I was in Nashville, Tennessee, visiting Vanderbilt University, and I had the opportunity to talk with Dr. Andrea Derdzinski. Dr. Derdzinski does a lot of work studying black holes and how they interact with their environment. In particular, she studies supermassive black holes, which can be millions to billions of times the mass of our sun. So, presumably the most massive black holes that can be found in the universe. A lot of her work involves understanding what happens when two of these black holes form a binary system and how we can detect these binary systems here on Earth. I'm Paul Duffel, and this is the Astrophysics Podcast. Yeah, so when I was in high school, we had there was a radio station in our high school, and it was like, and so that was like my vocational education as I learned how to do radio, and like I learned a lot about audio, and then I had to learn new stuff about, like, podcasting is the opposite of like radio, right? In radio, you're yelling basically. You're like, oh my God, we got this thing coming up, and like, but a podcast, you're like, hello,
I'm talking into somebody's earbuds right now.
Exactly. It's the opposite.
Yeah.
Anyway, all right, so you ready?
Yes.
Okay. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Andrea Derdzinski, who is a postdoctoral research fellow here at Vanderbilt University. Dr. Derdzinski, thank you for joining me.
Thanks for having me.
Okay, now, I know where we first met, but just to remind me, do you remember the first time we met?
I remember the general period of my life.
Okay, right. Because it would have been in New York.
Yeah.
So you were at Columbia.
Yes.
And I was at NYU. Or at least, actually, I may have already graduated by the time you started at Columbia.
You may have just graduated. So I started in 2014.
Okay. So actually, I might have met you. Did you go to a visit at NYU?
I visited as a prospective student.
Okay, then I probably met you then.
Yeah.
I think I may,
because I met with Andrew as well to do research with him.
And he usually goes like, Paul, come help me convince.
Yeah.
But apparently I wasn't convincing enough. You ended up going to
Columbia. Did it.
So that's nice. So then, But so anyway, that's how we originally met, and so you're when you were at Columbia and I was at NYU, and our advisors collaborated a lot.
Yeah,
and so we ended up talking a lot and working on things together.
Yeah.
So so the first part of this, I didn't tell you this in advance. That's okay. The first part of this will just sort of ask you about how you got into science and how you grew up and stuff. So let me start by asking, where did you grow up?
I grew up in Fairfield, California. It's like right in between San Francisco and Sacramento.
Okay. And so what was that like?
There was it's in a beautiful agricultural area, but Fairfield itself is very much just like a big mall, a Budweiser factory, a lot of suburbs.
Okay.
A cool skate park.
So a lot of what you kind of picture in when you imagine American suburbia.
Exactly.
That sort of thing.
Yeah.
All right. And so when you lived in Fairfield for a large part of your youth.
Yeah, till I was 18.
Okay.
Yeah.
And do you have a memory of like the first time you remember getting interested in science, or?
I think I liked science in general a lot as a kid.
Mm-hmm.
I mean, like probably like picking up bugs in the yard. If I'm going to go way back, astronomy wasn't a thing that I thought I would do at a young age. So I don't have one of those romantic stories of like looking at the stars.
No, you don't have to have one of those. I have plenty of those. That's fine.
Yeah.
In fact, Yuan Li had the same story about being really interested in bugs in the yard when she was a kid.
Yes.
But generally you like, I guess, were interested in science. I guess can you come up with an example, or?
Well, I think I just liked puzzles.
Mm-hmm.
Like literally, like when I was young, I had like books of like those word puzzles and mind Twizzlers. What are they called?
Right. Something
mind
like
twisters,
that.
I don't know. So I think I liked that aspect of it, just like the curiosity.
Right. So just things that worked that part of your brain.
Yeah.
So it wasn't specifically exactly the world of science. It was more your interaction with problem solving and
which isn't only in science.
Which isn't,
ironically, I discovered that later.
That's right. Yeah. We as a society, we kind of treat that as, you like problem solving, you should do STEM, you should become an engineer or something like that. But that's not all you can do.
Well, there's a lot of creativity involved. I would have loved to be in the arts or social sciences. I mean, there's a lot more problems.
Well, too bad you're a scientist.
Here we are. And now I get to be on Paul's podcast.
That's right. But so, what did your parents do?
They were kind of an academic family. My mom was a doctor, pediatrician, really convenient growing up, and my dad was a chemist.
Okay.
So he ended up working for a pharmaceutical company.
I see.
And I don't really know the details of what he did.
Mm-hmm. But they
projects,
but very educated parents.
Yeah, they were like, go to college.
Right.
Yeah.
But you enjoyed doing problem solving. So in school, you liked those classes where you were problem solving.
Yeah.
Stuff. So where did you go to college?
UC Santa Cruz.
Ah, okay.
Yeah.
Yeah, I must have known that at some point. But yeah, that makes sense.
Yeah.
But sorry.
You can forget. That's fine. It's been a long time.
That's all right. But anyway, So your parents were very STEM, or at least I guess they were very scientifically they were
very get a job oriented.
Oh, okay. I see.
No, they were educated. Mm-hmm. And valued higher education.
Mm-hmm. Mm-hmm.
I should say.
Okay. And so, what do you think? Okay, and then what put you in the direction of physics or astrophysics?
I don't totally know when the switch happened. When I was in high school, I did a summer program at UC Davis. It's called like the Cosmos program, which might be an acronym. I don't remember.
Okay.
But because it wasn't just astrophysics, but you could apply to go to college for 1 month in the summer and take short little classes and try a mini research project. And it had like biology, chemistry, some computational stuff. And I actually applied for the biology program, but then they gave me a spot in the astronomy one. So I did that.
Okay.
And in the end, I decided I didn't like it because it was too much computer stuff. Like I did an observational project.
Okay.
And I didn't like being on my computer all day.
Yeah.
Not that wouldn't happen in other fields.
It's funny though, because that reminds me of when I was like going like, I before I started grad school, I tried a lot of research projects, and I kept being like, I don't want to be on the computers all the time. I kept trying to get away from doing.
Now you're a computational astrophysicist.
That's all I do.
What did we do?
I don't know, but I kept being like, no computers. I'll just be like on a chalkboard drawing amazing things, and then eventually I really started to enjoy it. But I don't know if you had an experience like that, or if you just were like, you just gave in and said, "I'll."
I don't know. Yeah, it's like I wanted to master the thing I had the most difficulty with. I don't know. So there could be some weird psychological thing in there. But then in college, I was like deciding between neuroscience or astrophysics. They're both like these daunting fields where we know very little compared to like the vast scale of things. So I ended up just starting in astrophysics for some reason. I don't remember because I was 18. And once I started taking the higher level courses and learning about like transients, like supernovae and all these crazy high energy things in the universe, then I got really interested and started asking a lot of questions to the professors. And that led to me doing research, which was computational modeling. But then I started to see like, oh, you can make really cool pictures out of it. And
okay. So what if to the extent you can remember, what computational research project did you do back then?
I started with hydrodynamical simulations like I do now, but it was in the context of interacting white dwarf binary systems, which would be transferring mass. And so there was another graduate student who was working on models of how that could lead to some mass ejection in the system.
Right.
When there's unstable or super Eddington mass transfer. And so I did simulations. Is this an astrophysics audience or an everybody
it's
audience?
My parents. So
okay. Hi, Paul's parents. Well, what I did was simulations of like the outflows interacting with.
Right. So the idea was you had all this computational model of a bunch of gas around two white dwarf stars that were in a binary, and they're orbiting around and they're ejecting mass from the system, and you're trying to understand how that process works.
What does that ejecta look like? Because in the end, it ends up producing interesting structures that can produce weird radiation. So
anyway, that was way back when, before grad school even.
Yeah.
And so you were already doing computational modeling of gas dynamics, which you ended up doing now.
Yeah.
But that was, sorry, to remind me, because I try to pay attention, but I have my mind goes in lots of directions. But so to remind me, what was the original idea behind this? Was part of this? You got into this through the Cosmos program?
No, so the Cosmos program was just.
Oh, that's right. That was
during high school.
That was during high school. Sorry.
And then I had my senior year.
So it looks like I'm paying more attention.
That's fine. It's kind of early. That was during high school. I had my final year of high school where I was like applying for college.
Yes.
Decided I didn't want to go back to UC Davis because it was just cornfields. I got really tempted to go to Santa Cruz. And then they have a good astrophysics program, so I just thought I'd start there. And maybe I don't know how to change my mind after I choose something.
once you go like, I can do this until I get sick of it.
Yeah.
And then you never got sick of it, I guess.
That's a different interview.
Okay. But anyway, so then at some point during your undergrad, you got into doing research, a research project, and that was this computational modeling of this gas dynamics around white dwarf binary. And so then, so that, and that's kind of how you started. That put you on the path to doing astrophysics and computational work that you were trying to avoid for so long.
Yeah.
And then at what point, all right, in all of this, at what point do you feel like you learned how to be a scientist?
Oh, I don't know. That's probably like continuously learning to be really deep about it. I guess grad school is a big part of like learning to trust your intuition.
Yeah.
And that feels like the transition to being a scientist, right? To like be okay with not knowing stuff.
Yeah. No, that's a good, concise way of putting it. Just trusting your intuition in the sense like, I think when grad students just start out, they're not trusting their intuition. They're kind of scared.
Or you get too confident at one point. You think you figured it out.
That's right.
And then it just slowly shatters, like when nothing works.
That's right.
Yeah.
So they'll have some ups and downs like that, and then at some point you feel like you have a better sense of I guess the world you're in of doing science.
But I don't think it's been like a linear trajectory of me feeling more and more like a scientist over time. I think there's like waves of it where it comes and goes depending on like the people I'm working with, the place I'm at, what my level of motivation at that time compared to the state of the world being distracting.
Sure, absolutely.
Yeah.
So okay, and then what do you think that means? I guess that's a very that's a reasonably concise answer. But what do you think that it means to be a scientist?
Oh,
like seeing as how you're able to answer.
That's true. I should have an answer to that. I think, well, there's the job answer, and then there's the like personal identity answer.
Okay.
Right?
Yes. Like, in other words, there's the answer that I don't know. What do you mean by that?
Like I'm a scientist because I work in a science department.
Okay.
No, but what does it mean? Like, I guess that's not an interesting answer. Like, I guess it's having some and the thing is, whatever answer I say, there's going to be other things that also answer it.
Right.
So I'm going to walk myself into that.
Okay.
It's having some curiosity about how things work.
Mm-hmm.
And then dedicating time to trying to answer those questions.
Right.
That's not specific to science.
But that couldn't be specific. Yeah, there's more to it than that, surely, because many people do that in their day-to-day lives that aren't scientists. But yeah,
it's kind of a human thing.
Yeah, maybe that's
what I mean. It's like doing it formally as a job.
Right. So it means that's right. So it is a combination between this is your job to do it and do this, I guess, and your whole purpose is as your job, as opposed to other jobs where like your employer is like, now do this task
for profit
for some because it benefits me and I will pay you as a response. This is much more of a open-ended job where it's like, be curious about the universe. And
I guess in some sectors it is also like for profit, but still it is, like it embraces like, let's work on something where we don't know the answer and we don't necessarily know how long it will take to get the answer.
Yeah.
And it's like for the sake of trying to build an understanding.
Yeah. Purely, that's right. That's good.
The romantic answer.
No, that's good. I like that.
Yeah.
It's okay to be romantic. But yeah, it is, I mean, now I'm listening to myself not being able to finish my sentence, but yeah, it is. Answering a question for its own sake, not because of the thing that you're trying to get. There's not I'm
not trying to get the black holes to do something for me in return. I just kind of want to get them, even though I'll only get a tiny part, and then it might be proved wrong.
Right. That's right. Good. So yeah, that is a large part of this science identity. You don't really get like the payoff. There is. I mean, for some people, you get the payoff of like self-glorification of saying like, I'm the one who discovered this or whatever.
Yeah, that doesn't get me.
That doesn't get you.
No.
But yeah, ultimately it's really just I want to know the answer to this question or I want to help out the community to get the answer to this question.
Oh, yeah. The latter is more accurate.
Yeah.
Because if I were to do science by myself in a room, I would not be doing it. Like that's... I guess maybe I don't solely identify as just a scientist, and I really care about the connections with people. It's almost like sometimes the science projects are just like a medium for us to like connect and try and work together and collaborate and stuff. If that
and it can sense. Be, yeah. But you're right. It's a lot of it is like we as a community sort of decide what are the important questions to ask, and how we come to that is very much.
Arbitrary.
Yeah, there are some component
political,
to it.
I don't know.
There is some component to it which is arbitrary. It's not totally. I mean, you could be very cynical about it and just say that it's arbitrary. Or, my advisor once described it as kind of being like a Ouija board, right? Everybody's got their hand a little bit on it and kind of nudging things, but you're kind of just to establish. Hopefully, my listeners don't believe Ouija boards are a connection to the spirit realm or something, but people are all pushing on the thing, and that's why it's moving.
Yeah.
But yeah,
I get that. That's a good idea. Like because we follow as like a school of fish or something. Is that right? I guess I need to ask another scientist.
But yeah, there is. But in a sense, though, that means that there is an aspect of this is the sort of general idea of the community of what are the things that we care about and knowing. If
you start questioning it too much, you'll start to like fall apart, which I do every once in a while.
That's right. So let's move on.
Does it really matter?
We don't want to question it too deeply.
Cancel the podcast.
All right.
No, I'm kidding.
So now you're an astrophysicist. What do you like most about your job?
Ooh, that changes as well.
Mm-hmm.
Right now, I think it's again related to the people I get to work with.
Mm-hmm.
Like because a lot of astrophysics initially for me felt very escapist in a way, if that's the right word.
Mm-hmm.
Like I was like a grumpy, pretentious teenager, and I was like, I don't care about the planet. Let's study stuff that's out of this world. But that was actually a really isolating way to think about it. And now I feel like after years of that mentality breaking down, I forgot the initial point of where I was going with this.
What do you like about
what do I like about it?
Yeah. What do you like about your job?
I like the creativity and like problem solving aspect, puzzle solving. Even if you don't really solve them, you just make little incremental steps.
Yeah.
I like the flexibility of it in a way, like what we work on kind of changes and we revisit stuff. So it's not like something set like in a trajectory and I'm going to do A, B, C, D, D, whatever, and then I'm done.
Yeah.
It's like every step you like discover something new and remake decisions.
Yes, I like that too.
But I especially like, I think, the creativity and brainstorming with people aspect.
Yeah. Yes, absolutely. All right. Well, I'm scared to ask this question. Is there anything you don't like about your job?
How much time do we have? No. Practically the structure of the field being very competitive.
Yeah.
And the environment of academia being like kind of ironically not conducive to doing the work we want to do in some sense, that like we have to compete and rush with things,
right,
which can compromise your work.
Yes. Like I would say in academia's defense,
defend it.
I will.
Yeah. No, I'm open to it.
Other fields are, if you're not in academics, other industries are going to be very competitive and antithetical towards like, genuine curiosity.
Yeah.
So relative to that, it's pretty good. But you're right.
Yeah.
It could be better.
It could be better.
It's but you're right.
I don't want to settle for less.
Yeah.
Really, like I don't know. I think I'd rather think slowly and carefully about things.
Right.
And I produce more quality work.
Yeah.
Than feel like I have to rush on a timeline.
Yeah.
And constantly prove myself with proposals, which I get that's how it works to get paid to work.
Right.
But it's weird to have a professional degree and like a decade later still not have job security.
Yeah.
Like,
so and so it would be, and there are a lot of parts of that process that are clouded with basically strong personalities being very competitive and being like, making it difficult to just sit back and say like, well, we all want to know the answers to these questions.
And also it's just black hole. Like we don't need to be like so mad about how someone treats a magnetic field. It's okay.
Yeah.
So maybe, sometimes there's a bit of like elitism that gets threaded in there.
We definitely take ourselves too seriously and often don't take a step back and go like, we're doing like, we're thinking about incredible things, but ultimately it's okay if like if we spend a whole century not understanding black holes in the right way and then we have to fix it, that's really not going to hurt anybody. It's
actually kind of dope. I feel like shake things up a little. I don't know.
That's right.
Yeah.
That's right. So good. And so then, so would you say that's probably like the kind of, that's a root of a lot of the challenges in academia, is just the sort of a lot of the competitive nature or the...
Yeah, I think competitive nature.
And also different fields are different. Like transients, you brought up, like when you have to, when astronomers have to follow up, like, oh, this crazy thing went off. Let's all point our telescopes at it, and
days, yeah.
Yeah, and so like that can be extremely competitive because then like everyone wants to be the first one to look at this thing, and steal someone's telescope time to look at it, and
then like, they want to be the one that looked at it and the one that published on it.
Right, and so there's a race to get it out.
Yeah.
So then that. Definitely, inevitably the science is compromised when that happens.
And no wonder I study black hole systems that evolve on timescales of years.
Right. Right. You can actually, in one orbit, you can, that's enough time for you to write a paper.
Yeah, and let's observe it 10 years from now.
Yeah, exactly. I do like that about those systems, and planets have a similar sort of thing where they're one orbit is a year, well, at least for Earth.
Yeah.
And so it's a little bit more relaxed pace.
Yeah. Like human timescales are longer is good.
Yeah, that's right. When you meet a new grad student or a fellow scientist and they ask you what you work on, what do you tell them?
Oh, let's see. I work on really massive black holes that we believe to exist in most, if not all, massive galaxies.
Okay. So you generally work on what we call supermassive black holes, the biggest black holes that we know of in the universe that are at the that are living at the. You said they were at the cores of basically essentially every galaxy, as far as we know.
We think.
Okay.
Yeah, give or take.
And how do we know that? How do we know they're? Or I don't have to answer. You don't have to answer that question.
Yeah, no, I just asked a student that when they were preparing for quals.
Okay,
how do we know black holes exist?
Oh, good. That's one of those questions I'm realizing. Like when I'm on someone's thesis committee, I'll ask a question like that, and I'm like, wait, that's a really hard question.
I ask because I want to know.
Yeah,
I'm
exactly.
Like, tell me.
I ask because I'm curious, and then I go, yeah. But anyway,
we do take it for granted sometimes.
Right.
We have observational evidence from various telescopes that suggests really high energy radiation coming from tiny regions. So that's one piece of evidence that something is generating.
Something really compact is generating insane amounts of energy.
Exactly.
Good. I'm going to come back to that, but that's one of the big ones. Things.
I would say that's one of the big ones. There's also certain variable emission systems where we can look at it over time, and there's high frequency changes in the emission.
Oh, okay.
That would suggest the gas is moving really fast around a small object.
Oh, I see. So it has to be moving so gas, if it's changing on a short time scale, that it means sort of the characteristic time scales, the orbital time is really, really short, and so it has to be moving really, really fast. So maybe close to the speed of light.
Yeah.
And
how do we move it that fast?
Yeah.
We know that one way to do that is to have a really massive compact object, which would collapse to a black hole.
I want to ask another question because my listeners, my parents, will want to know, when you see something really bright at the center and you say that's a black hole. I always find that's a funny thing that we in popular science we don't usually explain.
It's not a black hole.
Is it we say it's a black hole? No light can escape it. That's why it's black. It's dark. And then we say we can detect them because they're the brightest things we can see.
Exactly. Yeah. We're detecting stuff around a black hole.
Right.
And saying that a black hole is in that region causing the gas to do those things is it's an explanation that works in many cases.
Right.
So we're looking at radiation near the black hole.
Right. Yes, very close.
But we're not
just
at the black hole.
Basically, just a bit outside the event horizon.
Yeah.
And there's a whole bunch of material orbiting around super fast.
Yeah.
And it's producing very bright radiation, and that's what we see in this compact source. So we're not actually seeing the black hole itself, but we, as a shorthand, we'll say we're looking at a black hole there.
And to be fair, there are other models of weird phenomena that could produce that kind of emission.
Right.
In other
words, when you see something bright and compact, you could make up a different model, and it doesn't have to be a black hole.
Exactly.
But the general consensus is that these are typically accreting black holes.
That's where the Ouija board has gone.
Has gone. Okay, good.
Yeah.
Oh, good. Okay, so generally you work on these supermassive black holes and understanding how they work. So, how in what sense do you work on? What does that mean?
Well, it actually connects to what we were just talking about with the stuff around the black holes. I like to think about how black holes interact with their environments because they don't live in quiet, isolated places by themselves.
Right.
Like the centers of galaxies can actually be really messy and full of like other stars or gas that can swing around the black hole or interact with it or feed into the black hole and have it grow. Then there can be other black holes that come in, like other massive ones or other tiny ones that are like remnants of dead stars. So I like in general to think about the interplay of all of these things. But, one at a time. Right.
No, good. Okay, so that's a good general summary of the type of stuff you work on. And so then what does that mean day to day? What does that look like?
Debugging. No, okay.
Join the club.
Yeah. Day to day, I have like a list of different kinds of projects that are, I guess they are all related to stuff happening around a supermassive black hole. And some of them are computational projects. So I want to develop simulations that make approximations to equations and give us an idea of what would two black holes evolving in some plane of gas look like.
Okay. So these simulations, these computational models of what's happening. So what does that look like? I know the answer to this. This is one of the questions. Sometimes I'll ask a question that I completely know the answer to, but I want you to answer it.
No, yeah, it's good to hear different ways of answering it. I mean, because what I just said was not day to day. That's like a framework.
Right.
Now let's zoom in day to day. I'm using and modifying and writing codes that would solve equations for like a certain system. So I'm on my computer running tests and observing or looking at the data.
Right.
How do I explain this more?
For example, like we were talking about gas dynamics, right? So you have put the equations of fluid dynamics, or the equations of fluid dynamics are in this code that are basically telling you how the gas should evolve in time. Yeah. And you basically the code will track where the fluid is and how dense it is in different regions and where it's moving.
Yeah, what's the morphology around the black holes? And that then can be connected to predictions of types of signatures we should see. So the idea is really to just try and make predictions for stuff that we could verify, maybe observationally or with certain detectors. But of course, you like start simple. So I'm not like putting two real black holes in plasma in a box.
Right.
You start with some simplified models to understand some of the fundamental processes that are happening.
Yes. Yeah.
Look if there's like instabilities or weird resonances in the gas or
things that we could lead to observaable, some phenomena or something that we could detect and look for in these observations,
and like verify that maybe there's some interaction that's happening, or maybe rule it out.
So give me an example of a project like that that you worked on that you think was interesting or impactful.
Yeah, I guess I can talk about the main topic in my PhD thesis, which was running these types of simulations of two black holes evolving around each other in gas, and measuring how they interact with the gas, but also kind of framing it into how does the gas interact with the black holes.
Okay.
Because as they move through it, it's also affecting the movement of the black holes.
Okay.
That's right. So it's like kind of moving through water is like an analogy where it's like there's drag in a sense, but
right. So in other words, the black holes are pushing around the gas, but also the gas is exerting some kind of forces on the black holes.
Yeah, the gas is also pushing around the black holes. And that can be interesting because if we want to make predictions of do the black holes eventually like merge into one, or do they never do that, it will depend on how they interact with their environments.
Okay. And so, during your PhD thesis, I guess what was like, what was the result that you were that you found, or what's an example of something you can learn from this?
Well, can I talk about gravitational waves now?
Sure. Yeah, absolutely.
Has that been introduced?
We can introduce it.
I mean, okay. What was really exciting about during my graduate school career experience, we had the first detection of gravitational waves. What that means is that we had these ground-based detectors How do I say this
That's
shortly?
okay. All right. That's
We're
all right.
basically interacting black holes produce like some perturbations in space-time.
Mm-hmm.
We figured out a way to measure these tiny perturbations via like systems of lasers.
So this was the LIGO
Yes.
detector, with the one in Hanford, Washington, one in Livingston, Louisiana. These giant detectors that are measuring these tiny ripples in space-time, tiny perturbations, as you said, to the fabric of space-time. And we understand those to be caused by black holes that are orbiting one another and inspiraling and merging.
Exactly.
And so,
that was a better way to say that.
So that's the backdrop. And what you were saying is that during your PhD thesis, the first discovery of those, was that the first discovery?
Yeah, the first detection happened.
The first detection happened during, that's right, that was
2014. That was announced in 2015.
It was announced in 2015. That's why I always get the number wrong.
Yeah.
Okay, good.
So that really invigorated the whole field, that in the sense that we demonstrated that we could detect these tiny ripples generated by inspiraling black holes.
Yes.
Now, if we think about doing that in the future with different experiments for supermassive black holes, we've now thought of, devised, proposed, and mostly funded experiments to do that in the future.
Right.
Okay, and what's exciting about gravitational waves is that when you detect that kind of signal, it tells you it can be connected directly to properties of the source where it came from. So you can learn about the masses of the black holes.
Right. Because you're no longer, you're no longer have to think about, there's some interaction with some surrounding gas, it heats up, it produces some radiation. Like there's all these intermediaries usually in astrophysics between us and the thing that we observe.
This is much more direct.
And with gravitational waves, right, it's much more direct. You're just directly observing the ripples that are caused exactly by these black holes themselves, not by some intermediary processes, really.
Which is amazing, because it gives you like really strong evidence for black holes beyond all the indirect evidence that we've collected for years.
Right.
But now we know that black holes, especially the supermassive ones, can still live in these messy environments.
Right.
And so what I was excited to work on, and some of the results that I published, were about how does that environment affect the black holes and hence affect the gravitational wave signal.
I see. So if the black holes are inspiraling, but there's a whole bunch of gas around, that causes a change in how they evolve and how their orbit changes with time, and so that should maybe imprint itself on the gravitational wave signal.
It could potentially. So that was what I wanted to investigate and make predictions for.
I want to back up for 1 second, because you were talking about supermassive black holes.
Yes.
As opposed to like the LIGO detection was like say 30 times the mass of the sun type black holes. Very, which that's a large mass, but it's not nearly as big as like 1 million to 1 billion times the mass of the sun, right? So, and that's what these supermassive black holes you're talking about. So presumably something changes when you scale up to that big of a mass, right?
The size of the gravitational wave.
Okay.
In a way. So you need to use basically a much larger scale detector to measure these gravitational waves. The LIGO interferometer is something like 4 kilometers in scale. Is that right?
4 kilometers on each side.
So if we were to then scale up by like a factor of 1 million, we want something that's like a few million kilometers.
Right. That's very big. So you need a very big detector.
The community for years has proposed a way to do this, which is to launch a few satellites into space that function sort of like the LIGO detectors, where they shine lasers at each other that reflect back and forth to measure deviations. Right, and so they can be spaced very, very far apart. Yeah. And so it's effectively like having a giant building in space. Exactly. Without the building, though. Yeah. So this experiment is called the Laser Interferometer Space Antenna, or LISA, and it's formerly a European Space Agency mission with NASA involvement, which has been selected as like a ESA mission. So it is adopted going under development. They're constructing teams to make the instrumentation, et cetera.
Okay. And so the reason you're thinking about so the idea is that LISA will presumably be able to detect these supermassive black hole binaries when they merge, which will be much which are on much bigger scale. But then the idea is because the cores of galaxies are so dense with stuff and gas and stars and other stuff that those could alter the orbits of the binaries and leave an imprint on the gravitational wave signal.
Yeah.
So that's what you did for your PhD thesis.
And just detecting a signal from merging supermassive black holes is one of the primary goals of LISA, and it would be amazing on its own.
Right.
And what I did was sort of expand on, well, if they interact with their surrounding matter, not only do you have evidence for massive black holes interacting, but you can also then trace it back to probes of their environment in a very unique way.
Yeah.
So it's like a bonus science objective.
You're going to be looking at these anyway.
You might as well learn the most from them.
That's right. That's
exactly.
right. That's very cool. And so, and so that was in your PhD thesis. So do you, in that sense, is that where you found had your most impactful work is on supermassive black holes and their interaction with their environment? Or?
I think so far, that for years it was thought, well, first of all, detecting gravitational waves is hard. So if we're trying to detect little deviations to gravitational waves, that's another level of hard.
Right.
The work that I did showed that there could be some more uniqueness to the signatures, and they could perhaps be more detectable than previously estimated. So since then, now one thing that really struck with me actually in the past couple of years is I remember giving talks on this, 10 years ago? Because that's crazy. Maybe almost 10 years ago. And it would just be one talk in a conference on other stuff. And sometimes the feedback would be oh, that's really cool, but sounds really hard. Now there are conferences dedicated to just detecting environment effects in gravitational waves.
Wow.
So it's been accepted as a possibility.
Right.
It's also something that's accepted as something we should address anyway, because it could interfere with other science goals, if we don't take it into account.
Right.
And there's a lot of promise in terms of having this unique probe of this plasma environment that we can't necessarily get otherwise. So I would say, that's been the most impactful. Since then, I've been moving on to how might these sources even form?
Okay.
So I've kind of tried to expand a bit.
Right. So then this is not even thinking about the event itself, but how do you get supermassive black holes into a binary in the first place?
Yeah.
All right. So how do you answer that question?
I've been moving towards really fun events where one of the black holes is really small.
Okay.
So those are when you have an extreme mass ratio between the massive black hole and the a stellar mass black hole.
Okay.
These types of sources can form in galactic nuclei because black holes can get scattered in.
Okay.
Towards the massive black hole. Pause me if I need to say this better, or you can say it better.
No, we'll come back in a second.
Yeah.
But we can go back now. We can. So the idea is in the core of a galaxy, you have a supermassive black hole. It's eating up a whole bunch of gas, but then there's also another black hole. At least there's probably a whole bunch of them. But there's a stellar mass black hole, much smaller, and it gets caught into all this environment that's falling in. So and so then I guess you're trying. Is this a mechanism to get more black holes to get eaten by this supermassive black hole, or?
Yeah, it's something that we expect under reasonable assumptions to happen.
Right.
It will produce gravitational waves that would fall into the LISA detectability range. And it can also serve as a really interesting probe of fundamental physics and astrophysics. So, the reason that is because the black holes orbit and make really interesting gravitational wave signals.
Oh, okay.
Yeah.
So in other words, it's a very different. The LIGO detections were of two very similar mass black holes, and they basically inspiraled towards each other and produced this gravitational waves. Instead, when you have such an extreme mass ratio, you think of the central one, the big supermassive black hole is almost that's like the sun in the solar system.
Yeah.
And the little black hole, that's like the Earth or whatever. It's just moving around, and it's much smaller mass. And it spirals in due to either interaction with the gas or releasing of gravitational waves, and it gives some kind of and so that'll give a different type of gravitational wave signal than these sort of equal mass type systems.
Exactly. It also gives really long-lived signals. They evolve more slowly.
Okay, because they spiral many, many, many times before they go in past the event horizon. Yeah. So you have a chance to catch like a whole bunch of orbits.
Exactly. There could be a lot of them that appear, and it would be important to characterize those signals. How often those types of sources will form, it depends on a lot of unconstrained physics in the centers of galaxies.
Right.
Like how many stars are there?
Just what's going on, what's happening in that party around the black hole at that time. And so it may be complicated to sort of model, but there may be big error bars on how often this can happen or what. But
so I've been wanting to try and take small steps towards understanding better what types of sources like that could form in different types of galaxies. And if there's a lot of gas, how does that affect that process?
I see. So in other words, there's definitely similarities into what you did in your PhD thesis, and that you're asking about black holes interacting with their environments. But now for these very extreme mass ratio cases and and their environments may be much more complicated than you were thinking about before. Yeah. Potentially.
Exactly.
So, okay.
So, I mean, it's definitely been moving on from like the PhD thesis was demonstrating these types of sources, if they exist, or supermassive black holes exist in gas and merge, they could produce really interesting signals. Now let's add other steps of complexity to think about how do they form? Does that mean they have more complicated orbits? What does the gas actually look like when we put more physics into our models?
Right.
There's like a really rich amount of questions.
Right.
To answer to like increase our knowledge there.
And it's always amazing when you have like different ways of like, you take a step back and go like, we're learning about how black holes work, right?
Yeah.
Where like when I was a kid, I always assumed black holes were just a made up thing, right?
Yeah.
They weren't. It seemed too.
I feel like I'm
crazy,
making them up sometimes.
Right? But what we're developing ways of like really understanding how they work and how they form. That's very cool.
Yeah.
Okay. Well, let me ask now another question, which is this is very shifting of gears, but in your opinion, why should we care about astrophysics?
Ooh, don't ask me. Let's see. Because sometimes I don't care. And I think, so I don't know if this is going to ruin the whole interview. I mean, people tend to say, well, it's like the fundamental pursuit of knowledge, which benefits humanity, sometimes directly and sometimes just indirectly because we learn about the universe we live in.
Well, if you don't say it with that voice, it's very convincing.
Okay, but I think I'm not always convinced because sometimes I feel like it really is just like it for fun. I don't know.
So I guess that's a different. So there's a separate question as to why you do it.
True. Okay, right. So why should people?
I don't know, but you feel free to answer it any way you want. But yeah, so there is a separate question of like maybe you do it just because you think this is really fun. You all like the same reason that you got into any of this. You like problem solving, and these are really interesting problems, right?
And it just keeps giving problems. The more you think you solve them, the more problems you unveil.
Yeah,
I mean, it provides a really nice perspective, of course, especially when you're studying something that's like so much larger and evolves on so much longer timescales than humans in general. There's something kind of comforting about that in a way. Like it's just like being curious about things beyond us.
Beyond our day-to-day squabbles and things that seem like really important, but then you're like, well, these black holes don't care.
Black holes don't care about your email inbox. Like, come on. So I don't know. I think just remembering to engage with that kind of curiosity is really meaningful for me personally.
Yeah.
And I think in a way that can benefit everybody.
Yeah.
To like step outside of your bubble a little bit.
Yeah. Yeah, that's right. Good. So what, I guess what's next that you think is, what are you most excited in doing for the future, or what thinking about or working on? Or
well,
I guess you're excited about LISA.
I am excited about LISA. That mission is really growing. The preparation for the mission is becoming established. There's a lot of questions to answer. It is planned to launch in the 2030s.
Right.
Which is relatively soon on the timescale of how many things we need to figure out.
I remember when I was a grad student and it was said it was going to launch in the 2030s. I was like, that's never going to happen. That's so far in the future. But it's not that far in the future anymore.
Yeah. Which gives me like a pit in my stomach, but like also is exciting.
Yeah.
That most likely, we plan to be around to witness that launch.
Well, then it's also exciting. It is sort of exciting to get at a point in your career where you start to see these really long-term projects that come to fruition that you didn't when you first get started, it's like, these are the telescopes that exist. Like these are all, this exists, this exists, this exists, and you kind of, as far as you can tell, they always have existed, right?
Yeah.
But then seeing and we're proposing to send, these spacecraft in this crazy orbit in the 2030s, and they'll all shoot lasers at each other, and you're like, okay, that's a
crazy sci-fi.
That's not going to happen.
Yeah.
But then seeing over time the technology developed for it, and the actual, they haven't significantly changed the scheduled launch date in that time, and
it all started with an idea, written by a few people. I think it was in the 90s, right?
Maybe.
And I mean, I think part of it is it's such a long time scale. It's really amazing to witness that, because for a while that project was interesting, then lost funding, then people were trying to modify it, then they just kind of stopped getting popular.
Right.
Then it was reinvigorated.
Right.
Right. People that have originally proposed the project, some have passed away.
Right.
And so you realize it's really we kind of work as a team of generations of people working towards future advancement. Yeah. We're already trying to plan what to do in the 2050s. To me, I'm kind of slow down, guys. Whoa.
Right.
I don't feel that urgency as much, but governments do, and they want to prepare for what to fund.
Yeah.
And it's really exciting actually to witness that. And I think even if I didn't, if for some reason I wasn't in this field anymore when LISA launches, I still love the idea of being a part of its development now. And I think you had a question initially that I did not answer because I forgot.
Oh, I don't know.
Okay.
I'm not sure. But I was going to ask, so the original question is what's, I guess,
excited
next?
to work on.
Yeah. And so then I sort of said, you seem to have a little bit of trouble thinking about an answer for it. So I decided to give you the hint on LISA, because that is a thing that's coming up, in the next decade or so.
True. So science-wise, that is my main interest. Although I kind of like that different doors can open as you go, and different things become interesting, and you can sometimes follow those trails. I think the other main thing might even take up more space in my mind these days is building the community to get there.
Yeah.
Because you and I can sit in a room and think about LISA and make plans and really cool ideas, and they might persist and become proven or disproven, whatever. But we need more people to continue to contribute and build the field to make it successful. And that entails a lot of thinking about, how do we train students? How do we recruit people? How do we treat each other?
Yeah.
How do we start collaborations that actually foster good work environments? That's really connecting more to the people aspect on the ground.
Yeah.
And that's the other thing I care about. And so I think that helps balance my career at the moment. The big questions, but also today, how do we treat our neighbors?
Yeah, absolutely. That's very good. Good answer. All right. So unless you have something else you wanted to say. No? Okay. So then I'll say thank you so much to Dr. Derdzinski for joining us. I had a lot of fun talking science with you, and I hope you'll join us again sometime.
Thank you, Paul. It's been a pleasure.
Of all the questions I ask on this podcast, the one that by far gets the most variety in answers is the question, why should we care about astrophysics? I think it's good to stay grounded in the knowledge that on some level, no, we don't need to know how our universe works in order to live out our lives here on Earth, but at the same time, how can you not be curious about it? So thank you so much to Dr. Derdzinski, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. If you want to connect more or have astronomy or astrophysics questions, follow me on Blue Sky at paulduffel.bsky.social. This music and all the music that you hear on the Astrophysics Podcast was written and recorded by Britton Ashford, and you'll find it on her album Trotter. All songs are used with permission from the artist and producer. Check out Britton Ashford if you enjoyed the music. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, professor of physics and astronomy at Purdue University.